salesman is like obsolete, right?
Good to see all of you. The game plan is, Jay showed me something. He used Desmos for the maximum multi-segment linear regression thing, which I thought, this is an extremely rare admission. It was better than Google Sheets, the way he set that up. So if it's okay, I'm gonna ask you to show. After that, I wanna start putting ourselves in the situation where we get a new problem, and can we design a dynamic programming algorithm solution to it? So in other words, let's stop the mode where I'm just explaining things, and let's see if we can actually generate these things. I still want to talk about it, but I then want you to solve a new problem with it. So there's going to be that, and I'll ask you to work on the whiteboards. So do you want to show?
Hope these work.
HDMI, or there's also this adapter?
Yeah, but more like they actually just work. Kind of like
You love them, do you, what do you use?
I don't.
You just don't. I'm gonna use a really previous sheets. Use that smart.
How many people know Desmos, that system? Is it
I don't
because
like,
they
you
don't
not like
my
extensive
background.
knowledge.
Everyone uses it. That's flyer back.
in high school?
Yeah, in high school, yeah, everybody like uses it.
It's like a graphing thing, right?
Yeah, they use it more for like graphing, like literally like the most basic, like
Yeah.
y equals mx plus b, like that's it.
Your wallpaper is great.
But it, this
Yeah, it's really
actually,
nice.
Ian, that's what I thought also. This was.
No, but like Desmos has so much depth. It's
Oh,
nice.
you mean the use is only just the basic?
Yes.
So, just kind of recap. If you remember, there's these formulas to get the slope and intercept of a set of points, like, or the best like thing, and then we have like this error thing, and the whole like part of the problem that we're doing is calculating these for different intervals. So like 1 point, like 1 to 4, 3 to 4. You guys remember it.
Mhm.
So what I did was I put this in the Desmos, all of these equations, all the equations that the notation is a bit weird just because you can't have like two of the same name.
The sigma symbols are gigantic in Desmos.
Yeah. So we have this calculating b for intervals I to j, and that's dictated by like this data.
Mhm.
This data point, which I mean, ignore those two columns. These are like the example that we did, and so then it gets the data between like it goes from 1 to 4, so it would get all that from I to j, which would be 1 to 4. It'll calculate a and b for it, and then calculate the error. And then we plot a and b here along with the data. So, and we could see if I like put this down to just have 1, like go from 1 to 1, the error is 0, and it just goes straight through the line. Yeah.
Do you have to use the sliders, or can you plug in the values from the function code? Oh, actually, no. You put I and j, so you have to use the sliders.
Yeah, you have to use the
I see.
sliders, and I have j limited so that it goes from I to 4. So so you can't go like backwards or anything.
Does it coordinate that? So like I cannot make I greater than j, right?
Yeah. So if I try and like increase that, then it goes to 2,
Oh, wow.
3, and then 4. But I can do like from 1 to 2, 2 to 3, or 1 to 4, and then.
Can you? Okay, this is great. When you're done with your explanation, I actually want to do that lecture again in 3 minutes because this is so useful.
And then if we look up here, this is kind of just like, I wonder if I have it up. This like, all the way at the bottom, this like error table, but just in a different form. We're just calculating for each. So you see like 1 to 1 error 0, 1 to 2 errors that, and then 1 to 4 is like 50.3, something something.
Mhm.
It just rounds it, and then so on and so forth. And then with the algorithm, we'd use that table, and then yeah, that's
Yeah, so this is actually, I did not notice when you showed it yesterday, so this is basically a one-dimensional set of tuples that represented what I had as a two-dimensional array of scalars.
yeah.
Okay, yeah. So do this for me. So these are data points, like 1, 2, 3, 4 data points. Oh, no, there's one here also, right? Or just 4 of them?
No, there's just
4 of them. Okay. The algorithm is, did you have a question?
Well, I was just gonna say you can even do a little more on the where you're actually plotting the red line. You can actually limit it, like
yeah,
to
yeah.
just be between
Yeah, I
the
did
points
that.
so that it doesn't. Yeah. So you
Yeah.
can actually see like where the line would actually end and then transition to a
Where it
different
would end.
linear
Yeah,
regression.
I can add that.
Yeah.
So that's actually, I want everyone to keep that in mind because I think as I gesture the operation of the algorithm, that's going to be really useful.
Mhm.
So the dynamic solution does the following. It says, so this is me sort of like turning the algorithm into a person. So you want me to find the best number of line segments to fit this data. Now, I don't want to go into either extreme. I have to maybe, but I don't want to. In other words, 1 might be too few and -1 might be too much. So what's like the sweet number of line segments that gets the good solution to show trends? So the algorithm says the following. I don't know how many line segments I will need, but I know there's going to have to be a last line segment. Because even if you have 1 line segment, that's your last one. So it says, from here, let me figure out where that last line segment starts. So it considers every point as the starting place. So then, if you could do this for me, can you do I equals 3 and j equals 4?
I equals 3.
And j equals 4.
Yeah.
So that's this?
Yeah.
I'm a little surprised because I would have guessed that this red line would be this.
Yeah. I think that's just how it like calculates the stuff.
I mean,
So-
there might be like an indexing error or something like that because if it's just these 2 points, if I equals 3, j equals 4, then the single line fit will be perfect. It just goes through the 2 points. That's okay.
Would it calculate it with that though?
Yeah.
Okay.
Yeah. But so you say, okay, so if I actually am interested in finding the boundary of that last line segment, when I'm focusing on these 2, I get a perfect score. But then I would be 1 less, j stays there. And then you do a line fit to that. So that would be the case where I equals 2, j equals 4.
Mm-hmm. Which
And then
that
it
should
says-
be I equals 2. That should be correct.
That should be, well, it looks like it's actually doing the whole thing, by the way. I feel like the sliders are not being obeyed by the functions. So it might be a little tweak.
It might be.
But anyway, so then you'd say, okay, well, what about 1, 3? Well, maybe the last line segment covers that. So then you say, okay, I'm going to consider that also. You're holding on to these things. And then you say, what if I were to do the whole thing? So you have 3 choices for where that last line segment starts. Now you have to quantify the goodness of this. This is where this actually kicks butt because you could say, so let's see, this is the one. So basically say, take that distance, square that, plus take that distance, square that, plus take that distance, which is hardly any, square that, sum them up. That quantifies the goodness of that last line segment. And then you say, by the way, if new line segments didn't cost anything, this turns into a mindless, greedy algorithm, and it connects every pair of points to each other with a straight line. So in other words, if you have 10 points, it says the best solution I can have is 9 line segments, consecutive pairs. And so for that reason, say, I could see you being greedy. It's going to cost you. Every line segment you purchase is going to cost you. So you're trying to minimize the error, and I will consider the cost of a line segment to be a substantial contribution to your set of error. So it forces the algorithm to pick few line segments, but then with few line segments, these distances grow, so it finds that sweet spot as to where that divide should be. Yeah.
For finding out or for figuring out what the cost should be, because if the cost is really low, then it would just do 1 line for between every point. But if the cost is super high, I would just do 1 line. How do you figure out the sweet spot?
Application specific, domain specific.
Is it like how spread out the data is that is going to determine it, or is it
I think
more-
that you actually have to make an educated guess as to what's a suitable C. So does anyone remember, like, there was a guy here who graduated 2 years ago, his name's Pat? Birch or something. He was someone's TA here. Anyway, so he applied this to figure out the instability in climate. That these things were actually temperature readings for every 70 mile by 70 mile grid location on the continental US. And he had 20 years of data, and each grid position having like a measurement for every year of 20 years, every day of 20 years. So then for every pixel of the continental US 70 miles by 70 miles, he basically did this. And his hypothesis was, as the climate gets more unstable, for a particular C value, the algorithm is going to have to choose, no matter the expensive cost of a C, a greater number of line segments per year. So at a fixed cost for whatever he chose, if the number of line segments the algorithm wanted to reveal the trends grew, that was a proxy for the growing instability of the climate. Yeah. So he had to engineer the right C value for that to actually work out. Yeah.
And was his like representation of that, was that 3D because he had time in there too?
No, it was 2D, and what you do is actually, I'm going to say this, if it doesn't make sense, I would love to talk about it because there's more to be done in that project.
Yeah.
20 years of data,
Mm-hmm.
and you have a data point for each day of each year. So that's 20 times 265 data points, let's say, for Ithaca.
Mm-hmm.
You then do this linear regression.
Okay.
And then you say, like, per year, how many line segments do I need? Let's say for 2000 it needed like 50, 2001 55, and so on. You actually do a straight line fit into that.
Okay.
And then you take the slope of that line and let that be the pixel's color in the final 2D image. So if that number is growing and you represent positive slope with blue or red, it was actually, and this is the one thing that I always say, like we are used to interactive user interfaces, but the art component kicks in when you're able to convey a bunch of information without the need for dials. And his thing was actually to reduce all that information into a 2D thing that encompassed time.
Right.
It was
Okay.
like one of the most incredible projects that I've actually
makes
supervised.
sense.
Yeah. So, but my point is this though. I think that the moment you can visualize it, these things are much easier. That's totally fine actually. I
Okay,
wasn't trying
yeah,
to
it's
say
a bit.
and I do use Google Sheets because it makes dimensions come to life. You can actually see them. But I have to admit, this was really better than what I thought I could do in Google Sheets. So
Yeah, I'll have to try and fix like.
you just have to debug it though.
Yeah.
Yeah. Okay. Where's my computer?
Oh, it's reading. Oops.
Or whatever, at the end of the day, it's all JavaScript. Let's say something bad to say that we solve this way.
I will go to the. No, you just come on. So I'm going to go to the official presentation for the book we have. There's something called the knapsack problem, which is we looked at it, actually we considered this, and I actually gave this as an example of why greedy doesn't work. But first let me bring it up and then I'll actually say a few things. Okay. So the knapsack problem says that you have, so there's a quiz at the end of today. And it's asking you something, actually this problem, the solution to this problem, but there's only 4 objects, so it's going to be easier than what we are seeing here. In fact, you don't have to even run the algorithm, you can eyeball it and kind of figure out the answer. If there is a challenge about today's quiz question, it's going to be understanding the notation of the problem. So what that means is, as I explain this table, make sure that the variable names make sense. So this is basically saying that I have 5 objects. And I have a carrying capacity that is represented by uppercase W. So then if my uppercase W, if I remember correctly, it's 11, I think. Yeah, weight 11. So do you see how the weights are here, WI? If I were to be greedy and I wanted to actually take all of the 5 objects, it would be 1 plus 2, that's 3, plus 5, that's 8, plus 6, that's already more than 11. I can't do that. But the thing is, I can actually maybe do these 2. That's 11, right? So of all the subsets that are at or under that carrying capacity, can you find the one subset where it maximizes the value of what you chose? And the values are coming from here. Now, this is basically kind of like me in saying in English what the mathematical definition is, I think what makes it really click is the following. Like, let's turn it into a dumb little game. And this is something I used in this class, so I'm not trying to be funny a second time. I'm failing a second time. So you have a bag over your shoulder, which its volume is the carrying capacity. Let's say 11 liters of stuff, or 11 units liters, doesn't make sense. And then you walk into this thing, and the landlord actually has made it convenient for you, has put like a price tag on every object in that house. And what you're doing is you're saying, well, you have a scale in your hand, or not scale, something that measures volume. And you say, here's this brand new set of sneakers, right? Like, you figure out the volume, the price tags on it. You have to make a decision, is that gonna be something you steal or not? So if you steal it, then your carrying capacity goes down. But the value of the sneakers actually is in your pocket now. If you say, thanks, but no thanks, throw that away, ooh, there's a diamond ring over there. That's actually awesome because it takes little space and has great value. So then you say, okay, I know what to do with that one. That's definitely going in. And I think I made the example of, like, was it like nail clippers or something? You see, like, used nail clippers. So this thing actually doesn't consume volume, but it really doesn't have any value. And I could see myself not taking it, although if that's the last object in the house and it fits, I could see taking that too, so that I can get that 1 penny value. But then you realize there are 2 dimensions that I could be greedy. If something has high value, I want it. If something has high volume, I don't want it. So that gives you 4 combinations. Things that are light or consumes little space, of high value, goes in it. Things that are big and low value do not go in it. Then the challenge is, what do you do that's something that consumes a lot of volume but has high value, or something that consumes little volume but has low value?
And when we talked about this last time, I think that I was confused about is, can you pick one of the, like, if you have a list of those 5 things, can you pick one of those things multiple times? Okay.
Yeah, so it's a fixed set of objects. Yeah.
But you can decide where you want to prioritize, and sweet value is like the most important.
Well, yeah, that's the thing. Like, you could be greedy in either of those dimensions. So actually, this is really important in the design of these things. So just hear me out here. Greedy is suspect because you could be greedy on value, you could be greedy on weight, and then you could see yourself like, backfires because the other one, the one that you're not considering, is the one that makes the key difference. Then you could actually, quote unquote, be smart and say, I'm going to divide the value by the volume, or the value by the weight. So you reduce the 2 dimensions into one thing, and then you act greedy on that. The thing is, you can't take like 3/4 of a piano. The objects actually are discrete units. Yeah.
I think also, like, the problem with that is, even if you put them down to one value, you can't do a greedy algorithm because that's the same as like the coin chain problem, where it's like you're just trying to maximize for that value, but if they don't like align in a certain way, you can have an imbalance solution.
I see the connection. I don't want to go too far in this direction because it might actually be the whole class, but I feel, or I remember I should say that if you are dealing with things that can be turned into rates or ratios, greedy does work. But like I said, like in the discrete objects, it doesn't make sense because I'd like to take the piano. It's going to leave no room. So can I take 3/4 of the piano so that I have enough? Like, you just can't do that. So that constraint right there puts an end to greedy. If you didn't have that constraint, so you're basically having like different forms of spice that has like, you can take any amount of it, I think the greedy works, but let's discuss that after class. So this is actually a telltale sign that if there's more than one form of greed and they have to collaborate for you to figure out the optimal solution, you can actually, that's going to backfire. The answer that it produces may not be the optimal one. So now I want you to think about the progression of examples, because this book is the one that I chose because it has by far the best coverage of dynamic programming. That really was the single reason why I picked it. Now the very first, if someone says like, what's the simplest dynamic programming algorithm you ever encountered? It's not one that we covered, by the way. There's something that is really trivial, but it is the first, the atomic dynamic programming, and it is called Fibonacci sequence. You must have seen it in math classes, which was created by someone by that name, used to model population growth of probably rabbits, right? So basically you say 0's Fibonacci value is 0, 1's Fibonacci value is 1. After that, the current Fibonacci value is the sum of the previous 2. Did I get that right? Yeah. Now, If you do that recursively, if you are calculating the two previous Fibonacci values of 10, so Fibonacci of 9 and Fibonacci of 8, you will recalculate Fibonacci of 8 when you are calculating Fibonacci of 9. So certain subproblems will be encountered multiple times. So if you do mindlessly recursively, even by 50, you could see the computer waits. If I remember correctly, like by 45 to 50, it starts to take a few seconds.
Are you saying the 9th Fibonacci number and the 10th Fibonacci number, or 9 and 10?
If I'm calculating the Fibonacci of 10, I need Fibonacci of 9 and Fibonacci of 8, right?
Well, isn't Fibonacci 0, 1, 1, 2, 3, 5?
You're good
Yes,
now?
I'm good.
Yeah, exactly. And I think I was looking for some white space, but I think it's good. So this is 0, 1, 2, 3, 4, 5, 6, and so on. So these two are base cases, and then after that it's the sum of those two. 1, 2, 3, 5, 8, and here it actually, the value exceeds the index. The point is, this hinges on that, and the calculation of this hinges on that, and this guy's calculated twice, and that happens along the number line. So if you recursively implement this, it is actually shockingly, I did this as an example, I'm not trying to be funny, I literally did this. I can implement it recursively holding my breath. It's that simple, and you might be surprised about how quickly you could also do it. Like you could hold your breath and implement it recursively. There is no way I could do it iteratively, because you have to remember the last two values, and there's always like a matter of like, where do I increment it, and it takes a few minutes. So it's one of those cases where if you want students to understand recursion and why it might be an actually elegant solution, this is the perfect example. But then it's very inefficient. So Fibonacci of 50 takes a long time, like multiple seconds. And as someone who never played games, who's impressed by first-person shooter graphics, I'm looking at this thing, and there's this amazing world, and you're doing all these things, and then Fibonacci of 50, and the machine is tired. It makes no sense. And that's because the redundant recalculations is disproportionately larger than the actual work being done. So, yeah.
By the way, an interview question I got was to make it dynamic.
With Fibonacci?
Yeah.
And what's your answer?
You just memorize it like every other dynamic programming question.
Well, you memorize it though, so that is the right answer, but I feel like it's lacking. Like, tell me a little bit more. How do you memorize Fibonacci?
Like just with like an array with the index being like the number and the value. Like I don't know.
That would work. I would argue it's an overkill. That would work. Can someone tell me, like, how do you memorize that problem? The reason why it's the first problem is that the memorization is trivial. Yeah.
No.
But look at this. So, basically these are the two base cases. Is index is 0 or 1, the Fibonacci is the same as the index.
I was gonna say you could maybe have a loop that steps like two numbers in a time so that you don't have to
Basically you say like, if it's 0 or 1, it returns the index. Or if it's not here, you have a for loop that goes from here to here. And then it calculates the next Fibonacci number from the last two it calculated. So you have to have, in linked lists, in data structures, remember like the last pointer as you're traversing a linked list? You have last and second last, but not for pointers, but integers. So you say current value is equal to last and then plus last, second last, and then you shift them. And so you just need two integers. That's why it is the smallest, cutest, and easiest to understand dynamic programming, because the memorization is two integers, just two integers. But it does take, I said a few minutes, but maybe 5 minutes for me to debug the damn thing. It was like shocking, like and offensive, like how long it took me to get it right, but the recursive one was fast. Anyway, so you say that's my first dynamic programming. I would argue then the next one is the binomial coefficients, and choose k, and choose m. So that one also required two previous values, but those things came from a two-dimensional array. So where you cited as for the previously calculated values, it was always like in the Pascal's triangle sense. One is this side, the other one's that one side. So the positions of the values that you needed to calculate the current one was in particular directions of your past. Then comes the first one in the book, which is weighted interval scheduling. You did that one, right? In that one, you say, what do I do with the last one? And in both cases, you have to cite the previously solved solutions of that not being included versus that being included, which ruled out a few other things. So that one depended on two things in the past, but unlike binomial coefficients, their locations were not fixed. The previous array told you how far you had to go back, so it was specific to the data. Now, I love this way of classifying it because unlike everyone on the internet who think that you have to understand dynamic programming because you will come up with one question, they always throw you a bunch of them without a conceptual progression. Fibonacci is first. Binomial coefficients is next. Like, it's getting more complicated. Multi-interval schedule, weighted interval scheduling is third. The fourth one was multi-segment linear regression. So what was the additional complexity? It no longer was, do I include the last one or not? It was, where does the last one start from? So that was no longer an if statement, but a for loop that contains an if statement. But then the rest was the same. So now here we are dealing with the next one, that the book beautifully explains. In some cases, you actually have to generate a dimension over which you have to do this logic. So let's actually look at the visual and see if anyone can actually understand this. This, to me, just kind of like, not confession, but like sort of honesty, I guess. I've never seen a slide that is as understandable as this and as difficult as this, and at the same time. I just sort of get it instantly, but then I always get tripped up about the way it processes. So let's see if you can look at this and see what they are doing. Yeah.
I think they're varying weight limit because once you take an object, it's kind of the same solution as if you have that object and you have a lower weight.
So that's great. That's at the essence of it. Those of you who might be more detail oriented, I'm not that, by the way, but you could have said, like, what's going on there? Two values. That's the first time we're seeing an out function with two parameters. So this is actually what the book says. The problem says, given n things to steal from, what's the best subsets to steal to maximize profit? You could say opt of 5 will be like, what's the best you could do with 5 objects? Here's an opt function that actually had to invent a variable which accounts for decreasing carrying capacity, which is what you are saying, okay? So let's look at the parameters here. How many, the n value is 5 here. Why? Because here's 1, 2, 3, 4, 5 objects. It's 5 triplets. So this is the object ID, this is the value of it. So in other words, if I break into a house and steal object number 1, my value is like $1, right? But if I were to take the last one, it's $28. If I take like the second and the third one, basically the money that I go away with is 24 because it's the sum of these two. So if I were to take these two, what was diminished from my carrying capacity? It's 7 because the volume they take is 7. Is everyone okay with the notation? Because the quiz is based on it. Yeah.
Can you have multiple of the same item?
Oh, you cannot. Yeah. And there are versions of that problem also. So that would be a type of an object as opposed to an object. I don't know if you remember, but in discrete math we had like how many ways can you get like Cokes and Sprites and dipepes? So in that case, you didn't have one can of each. You had a vending machine that has like, this is not that. This is just the objects that you are given. So the obs actually did. Yeah, go ahead.
Can you just explain like exactly what like the graph at the bottom is exactly showing? So what it seems to me is that each point in the graph, each xy is just like it's the value of the total things you could get with the amount in the subset with the designated like weight limit at the top, right?
Mm-hmm.
And then so what are the arrows showing?
It's the way that you're actually traversing the search space.
Okay.
And that's technically an answer, but it's meaningless. I have to say a lot more than that.
Yeah, you did.
But I do want to point out one thing though. At this level, computer science education sucks. Like nobody actually spends time. Everyone spends time at their CS1 level, and I can show you the perfect artifact. The top of the problem is when the carrying capacity is maximized. That's the top of the problem. They put it on the bottom row. So when I'm talking about like top down, I'll talk about the top down solution to this, and I will gesture it this way. Right? Make it harder, like it's almost like adversarial. So when we are doing this, we might actually want to kind of flip this, but this is the top of the problem. And what it's saying is, if you focus on the first column, this is saying that, look, the whole thing is too complicated. I would like to have the consideration of what I can do if there's nothing to steal in that house.
Mm-hmm.
This is like only the first object is what I have in the house. The first two objects. So with that in mind, let's actually look at the numbers. So carrying capacity is 11. Again, I saw that earlier. So if you have nothing to steal from, this being the values for your carrying capacity, initial or how much is left, doesn't matter. Doesn't matter what objects I have at my disposal. I don't have a bag. I forgot my bag. I can't steal anything. This one says that you are considering a place you broke into that has one object.
Mm-hmm.
Which one is that? This one. So it has a value of $1 and it consumes 1 unit of volume. So that would mean that if my carrying capacity is 0, I cannot steal it. But as soon as my carrying capacity goes up to 1, I can steal it. But because there's nothing else in the house, as my carrying capacity goes up, this value doesn't go up anymore because the one thing that I could have stolen, I stole it already. Did that make
Right.
sense, Ian?
Yes, yeah.
So I'll do 2, the second row, and then you do the one after that.
Okay.
You don't have to.
Alright, 5 bits.
Yeah, so this is basically, I broke into a house, it's got 2 things.
Mm-hmm.
And my carrying capacity is either 0 or 1 or 2 or 3. Let's see what happens. So if I have no carrying capacity, I can't steal anything.
Right.
As soon as it goes up to 1, of these 2 objects, this one fits. So I throw it in, I have no capacity left. So for that reason, the maximum that I could do at 1 is going to be 1. But if my carrying capacity was 2, all of a sudden the second object fits in it.
Mm-hmm.
And now I have to think about like which of these 2 do I take.
Right.
Now carrying capacity, sorry, I was pointing to the wrong thing.
Yeah, you're on 1 and 2.
Yeah. So this is when I can take the first one, if the first one
Right.
fits.
And
I
then
can
that's
do-
when you can take the second one, but not the first one. And then from then on, you can take both.
Exactly. And then
Okay.
after that, I can't go any further because I
Right.
don't have anything else to steal.
Okay,
So
that makes
that's what
sense.
they're doing. They're saying that, look, consider, again, this is take a value of the problem, which is your carrying capacity, turn it into a dimension,
Mm-hmm.
this dimension, and then say, let me consider this problem in stages where the base cases are, no matter what the carrying capacity is, there's nothing to steal, 1 thing to steal, 2 things to steal. Now your question as to what the arrow means, if I'm over here, and this is kind of like borrowing from what Dob said, the ideal answer here is going to hinge on 2 considerations. In some ways, this is actually like weighted interval scheduling in some ways, but yeah.
So
Seems like it.
At least of this one structure, the number that gets the subset of items that to decide the order of which you include them is based on the weight. Is that true to assume that you'll sort them by weight and then index them by that weight? Or
That almost was going to be some question I asked you guys at the end, like, does it need to be that way? The answer is actually no. It works no matter how you organize it, because this considers all possibilities. Although this makes it easier for a human to comprehend. I should say, the ordering of this is insignificant, although a particular order makes it easier for us to comprehend it.
Okay.
Yeah.
I was curious if you sorted them by value and then tried to do like a divide the problem into like a maximum subsequence or each section in seconds.
Because of the independence of the volume and the value, there are cases where that backfires. I mean, what you're telling me is still sort of like a greedy algorithm. Yeah. So I just want to show you what this is saying. If I'm actually here, here's the question I'm asking. My carrying capacity is 11, and these are all the objects that I could steal, right? So what's the difference from here to here? It's object number 5. Right here it was 1 through 4, here it's 1 through 5. So basically from here to here, I'm making the decision, do I take the 5th one or not? Now, if I go directly up, that means that I did not take it because you didn't move horizontally. In other words, the act of choosing the 5th one has, the act of making a decision about the 5th one, if it doesn't change your carrying capacity, that implies you didn't take it. But if you take it, going from here to here, not only there's going to be a value that you acquire, but your carrying capacity will diminish by the volume of that 5th object. So that would mean that in every one of these boxes, I'm saying either I go straight up from where I am, because I'm just rejecting that object because it doesn't seem to be good, Or as I go up, I am actually not overlooking that object now because I convinced myself I should take it, but then I have to go horizontally to what the new volume will be because now I'm carrying that thing. Does this make sense? Yeah.
I feel like I've asked this before, I just
That's
wanted to
fine.
confirm it again. Is the goal to take as many items as possible, or just items of the maximum volume as possible?
Second. Yeah. And the structure of the book is, if it had been objects of volumes, but everything was equal value, you could do this greedily. Or if all the objects have the same volume, but they change by value, you could do this greedily. But then when you have those two considerations not necessarily cooperating, then you have to actually be wiser than greedy. And this is basically that. You're navigating in a two-dimensional sense because one dimension expresses how you are losing capacity as you're pocketing things. And the other one is actually saying, how do you actually solve this problem with fewer objects? Does anyone have any questions? Because I feel like we should kind of like work this out, but we'll flip the problem so that the top of the problem is actually top of the screen.
It's not really a question, but so because from the second 40 like going up,
Mhm.
the line goes over to weight 5. That means that you took item 4, and so the amount of times you go to the right, that's the amount of items you're going to have, and then
Yep.
the item itself is the one that gets removed.
That's excellent. The number of times you go from one row to the next where the arrow is actually going somewhat horizontally, that implies an object being picked up. When you go straight down, that implies that that object wasn't taken. So let's figure out what they thought was the ideal answer. That would mean, so it looks like I actually didn't take this one. So from here to here, that's actually this, right? This means that I actually, going from the case where 3 was included, going to the case where 3 is not included. If that progression is horizontal, that implies loss of carrying capacity, which means I must have picked that object. So this is 3, right? So the value is going to be $18. And then it looks like from here to here, there's a horizontal movement, so that means 4 was included. So that's 40. Right? So the solution is claiming that the maximum you can get is 40. So I said, I could do better. I'll take the last 2. That's, what is it, like, that's 50. But 6 plus 7 is greater than 11. So this solution is saying that, and we can actually, I think that we should kind of work this out. But here the solution is only those 2 objects will maximize your what you will steal. Questions? How does it actually, do you think that if I gave you, if we change the parameters, do you know what the solution should be? Or can you try it at least? Like, do you not understand enough to attempt the solution? If the answer is no, I'm happy to explain more, but I think that if the answer is like yes or likely yes, I think we should just try it. Okay? So let's change these numbers a little bit. Let's do this. Let's say that this is 7. Let's say that this is 10, and let's say that this is 15. Okay, so the values are redefined. And now my question to you is, what is the optimal solution here?
Weight limit is 11.
What was that?
The weight limit is the same.
It's 11. We could have changed it, but I feel like this is going to make it a little bit more magical. So could you please, let's see, we have 8 minutes left. Let's get that out of the way, and then I really want you to attempt this because attempting this is more meaningful than the quiz question. Can you eyeball this and really quickly answer it? You could just use your human perception to solve this problem, not to unravel it. So, real fast, what's the meaning of this?
It's the weight.
Yeah, that's
The
your carrying
weight.
capacity. What's the meaning of this?
It's just the max items.
4 objects to steal from. And you have to interpret these things. So it says the format is VIWI, value weight. Those are the values. And if you choose to go for this $2 thing, then your carrying capacity is compromised by 3, right? So can you actually quickly figure out like what would be the ideal subset for this? But don't yell it out. I just want to have everyone to have an answer, and then we'll just be done with it, and then we'll attempt a big problem. Give me an indication when you think you have an answer. Okay, there's 1 hand, 2 hands. Is that a question or an answer?
Oh, answer.
Answer. 3 answers. I'm gonna go up to like 7. That's a nice prime number. Like, so we're at 3 right now. 4? Okay. 5?
Okay, thanks.
6 and 7. Alec. Alec, you have to answer my email. Not just yet, but now, like, you know. And Dana, you have to answer my email. So count to 3, and then you yell out basically the answer. So it's going to be like one of these 5 letters, A or B or C. So count 3, and when I would have said 4, you tell out the answer letter. 1, 2, 3.
D.
Nice. Yeah.
There we go.
It's 8, yeah. So that would mean that you select,
Yeah,
I think it was these 2, right? Oh, the
5 and 3.
Yeah, yeah.
See.
Okay, so I want to actually think of it this way. I don't think I have time to actually pull up the spreadsheet. So, okay, Jagrid, your way of doing would go this way. Because of the way that this is rendered upside down, this way would be top down, right? But it's actually the bottom up solution.
Yeah.
It's going from the base cases to the original problem. This way is actually going to be the recursive one. That's top down, but I'm actually gesturing this way, so keep that in mind. So if I'm over here, that would mean that I'm deciding the fate of the 5th object, right? So this would mean that I do not take 5, but this would mean that I did take 5, and so where would this arrow go if 5 was taken? Yeah.
So 7 or column 4.
This
Yeah.
one? Okay. So what we are doing is we're saying that I know that the answer, the ideal answer to this problem will be the better of what I find here, or what I find here plus the value of the 4th object, which is 22. If you understand this, you have this.
Isn't that what you took the 5th object?
Yeah, you took.
Oh yeah, 22. Yeah, thank you. Yeah, this is the pattern. You're saying that I don't know what the answer will be, but I know that it's going to be the better of the following 2. Either that number, which means that I just didn't care about the 5th object, or I did care about the 5th object. I stole it, but my carrying capacity was reduced by the weight of that thing, which is here. So then over here, I say, I don't know what the answer here is, but it's going to be either that one, which means I didn't choose to take the 4th one, or, gents, if you can see, actually I picked the one person who cannot see. Can you see it, or should I go with someone else?
No, I mean, kind of. What were you gonna ask?
Like, if this answer is going to be the best of this one, or which one?
It'll be. Yeah.
Yeah, so anyone? Fisher?
It means you didn't take object 4.
And so the arrow goes where?
Up
Up.
to.
But like how far horizontally?
Oh, wait, what? You're saying if you
You
choose
say if
take
you-
object 4?
If I take the 4th
Oh, then
object.
it'll go where the red arrow is pointing. 18.
18, but we changed it, remember? Like I erased them.
Oh, it was
Sorry.
7, 10, 15.
So yeah, I think that, like, what is it now? It's 48.
So the answer would have been you taken object 5, 2, and 1, right?
I don't know which ones I will pick, but because, so here's, this actually, and this is not like a wasted opportunity. I think I can actually just get to the punchline real fast. For every box, you will consider the better of 2 choices. Either the number above you, or the number from the row above you, but to the left by the weight of the object associated with that row. So
Mhm.
you always have things like this. Like your visual is always going to be like this. This is the problem. It's either that or that. This is the weight of the object associated with that. So now we have 2 subproblems, this one and this one, right? So here, this ideal answer is going to be either that, or that, right? And this one's gonna be either that or that.
Right.
So for each of those, you'll start doing the same thing, that, or that, or that, and I did that intentionally. You could see how the same problem comes up multiple times.
So
if you cache it, it's all one. If you don't cache it, it's all
yeah.
one.
So when you're going up, like in the graph, it's essentially like just like looking at the subset without the element that you just basically.
Yeah. Yeah, as I go from one row to the previous row, if I go vertically up, that means that the object that distinguished them, I choose not to take it.
No.
Are there any questions? Did you understand this?
I think so.
Okay, I think that if we are able to do this, like this wasn't the only thing we did today, so that's actually quite good. Like I said, this is, if you encountered that, Mr. Atticus, as the dynamic programming question, like Fibonacci numbers, that shows you the state of things. Like that's actually so simple that you should not dignify that with an answer. Like back in the day when Google was interviewing, the on-site interview, if they ever asked one, it would be along these lines. So you guys are actually killing these now, so this is really, really good. But I do want to make sure that you understand it and just simply nodding when I'm explaining it. So if it doesn't click, you know where I live, okay? All right. Yeah, Julia.
When will our final exam be on time?
Hey guys, I feel like I'm ready to call it. Like Dana, do you know like there are some, I think that, yeah, can I just send an email about that? Yeah. I already put you on the spot, for which I apologize. He's also on the spot. He doesn't care.
What do you know?
I need to work hard.
Okay. I think majority of people are okay with the Monday.
I'm good with the Monday.
Yeah. Now you have to understand, like, you know, of the small subset of people yet to answer, if at least one of them says no, I cannot change it.
Well, there's an algorithm for this, for sure.
My algorithm is just what I said. If there's one objection, we're not doing it.
Yeah, exactly.
It's an 01 operation.
I trust you, but I'm not fully